want to go back now a few more years than Ray. As you've probably gathered, I'm a paleontologist, but paleontology is simply a branch of geology. So I'm a geologist first and a paleontologist second, and that's what you do your degrees in. The rocks around here, if we were to go down maybe 40 or 50 meters, we would meet rocks that are Silurian age. And that means that they are Paleozoic, and Paleozoic literally means old animals. Okay, so that's when the first animals began to occur on Earth in any numbers. Now, of course, those of you who have studied a bit of this will know that the things were around prior to the Paleozoic, but the Paleozoic is when it really began to happen. But what's interesting about the Silurian here is that this part of the world was one of the few parts of the world where plants invaded the land. So we are standing on rocks that almost certainly have fossils in them that represent the first plants on land. Now we can't see them, but they are very common in Victoria. One of my PhD students, who surprisingly is Irish, he came out here to study these. There are 3 places in the world where these occur. One in Cork in Ireland, the other one in Victoria in Australia, and the other one is in China. And those 3 places in the world are where the first plants began to colonize the land. Now what's important about this is if they hadn't done so, there would be none of us, because you can't have animals on the land unless you've got something for them to eat other than other animals. So it's part of a sequence of events that began, and this is where we are talking 400 odd million years ago. So a long time ago.
Do you know why they did?
Well, it's a very good question. I don't know whether you heard the question, is why did they bother to come on land?
I didn't know spots.
Well, they may have done it in other places. They may have done it in Scotland, in all sorts of places, but the fossils aren't preserved. And that's one of the rather interesting things. The chances of a fossil being preserved and found is probably something like about 1 trillion to 1. So it's very unusual. If we were to all, die, let's use that word here, and our bones were here, they would be scattered, they'd be chewed up, they'd be lost, and almost certainly nothing of us would remain. So why do some areas get fossilized? Well, I've just been working on a very interesting place in Slovenia, where it's actually called a Conservat Lagerstätten, which means it's another German word that means it's a very unusual preservation. And what happened there is we've actually got preserved on pine cones the little wee first settlement phases of things like barnacles. Now we don't normally get them preserved. If we were to go out there and look for them now, we probably wouldn't find them, they're that rare. But these things were preserved on pine cones, and you say, well, that is very interesting. How do we get barnacles on pine cones? So how do you think we do? Do pine trees live in the water?
Have to fall into the water.
Yes, the pine cones must have been washed out into the sea and sunk to the bottom, and then there they were colonized. But this paper came out last month. And it's really interesting. When you publish something that's unusual, you get people from all around the world asking for copies of the paper. As I was saying, the reason for pointing this out is that to get things preserved like this is very rare. And to get plant fossils, first land plant fossils preserved, is very rare. The ones we have in Victoria are very small. They are not big trees like we see around us here now. If we were looking at ancient Victoria, we would find it was typically with lots of things like mosses and liverworts and things low down. But what happened then is quite interesting. Things in the sea thought, hey, there's a table of food out here. So they began to come out and to feast on this table of food sitting out there. And they began to develop techniques which led to them becoming air breathing. Now, this is a lot. I wasn't intending to say any of this, but it's just because it's because we had this little spot here, and it's quite nice. One of the things that we try and do always when we take people out on a walk like this is to interpret things, do what we call park interpretation, and to look at nature and to say, well, okay, what does it mean? You know, how can I work out what happened? And even if we just stand and look at what's at our feet here, what is it? What is that down there?
Sand.
Sand. Yeah. Now, why is it there? I mean, it's a really dumb question, you might think, but it's actually not as silly as it sounds. Why is the sand there? Now, some of you may be associated with the Bayside City Council. You might say, well, okay, there's a crushing plant and they bring sand and they dump it on the beaches and it gets washed up. And that's true, but we don't need Bayside City Council to get sand here. What is the sand made of is really interesting. And if we were to pick some of it up, we can look at it. This is one of the most important tools that a geologist has. It's a jewelers call them a loop, but it's a hand lens. And this one is the maximum a geologist should have is about 10 times. If you want to get any bigger than that, get a microscope. And if you want bigger than an ordinary microscope, get an electron microscope. Now, this stuff down here, if we pick it up, a little bit of it, it's quite interesting. If I look at it, it is remarkably consistent. There is only one mineral here, except for a few bits of ring-ins of
Humus.
yeah, exactly, humus, yeah. It's all, what is it? Anybody tell me what it is?
Silicon.
It's quartz, yeah, silicon dioxide. And why is it silicon dioxide? Why is that here? Why don't we have beryl or feldspar? Feldspar is the most common rock-forming mineral, but it's virtually absent here. Why is that?
Because
Pardon?
It's not volcanic, it's sedimentary.
it's old.
Well, remember that when rocks corrode, it doesn't matter, this stuff here is produced by weathering and erosion. It doesn't matter what the rock is. Ultimately, it ends up with what we call detrital minerals. These are tough minerals that survive. The clay has all broken down to form, this feldspar, the most common rock-forming mineral, has simply broken down to form clay. But where is the clay?
Oh, so is it shells?
No, this is silica. The shells are made of calcium carbonate.
Yeah, true.
The clay has gone. It's been washed away. And that's accumulated, hopefully up, away from Beaumaris. Anywhere but Beaumaris.
What, in Brighton?
I wasn't going to say Brighton, but as you may or may not know, the waters carry sediment along the coast in two directions. In winter it goes that way and summer it goes the other way. So it's quite interesting. It moves backwards and forwards. And when it's moving this stuff here, it gets rid of the clay. And eventually we have just this beautiful quartz sand. Now what's quite interesting is we can get down on the beach here and we'll see areas where the quartz sand is just like sugar crystals. They're around about 2 or 3 millimeters in diameter. And what's happened is it's been sorted. Now before we go down, let's look at the rocks over there. These rocks over here, the rocks we can see behind me, are called the Beaumaris sandstone. Now sandstones are made up of sand, but they are also stones. So why is that? If we were to have a look at that one there, under the hand lens, we would find that it was very similar to this here. But why is this loose and that solid? Now you can't answer the question because you've probably heard me say it before, Pete. Pete's a little bit difficult sometimes. He gets... So if you just say to him, that was well answered, Pete, he'll be happy. So why is that rock and not sand?
Compression.
Pressure's a very good answer. It's a very good start. And if we were to get a really big press You can do this, and I've seen it done many times. You can put this in it and press it down, obviously with a machine rather than just by hand, and you actually get a little disc of what looks like rock. Then you put it in water and it goes pew again. Yes, you certainly may.
Because it was sort of like a subterranean layer that was pushed up. You know how the different...
You mean like a volcanic eruption?
No, I was meaning more like, you know, when there's
Folding
a shift
and
in the
bulging.
plates and all that stuff.
Folding.
You mean yes, a tectonic activity. You mean
Yeah.
subduction, the opposite of that.
They're big words.
They are.
I
Well,
think you said something.
Well, I
That's-
said folding
that's-
and folding.
yeah, that's actually making it a lot more complicated than it needs to be.
Oh, good.
So really, if you wanted to make this into rock or stone, you could heat it, and it would then be very hot, of course, and you'd have to have a blowtorch. But much easier than that.
Mix something else in?
What was that?
Mix something else.
Yes. What would you mix with it?
Clay.
Glue.
And what kind of glue?
Not PVA, because there are. Well, you know, there are natural glues out there that we can find very. One of the most unusual is clay. Clay actually will glue things together. But the ones we've got down here, we don't need clay because we've got a whole lot of other things floating around. See the colour of that rock there? Is that a different colour to the sand? What colour does it look like? Pardon?
Okay.
Iron? Who said iron? It looks like iron. In fact, it is iron. But it's not iron metal, it's iron oxyhydroxide. It has the formula, for those of you who are excited by chemistry, a big F, a little E, and then you put a dot in, and then an O, and then another dot and an OH. So it's iron oxyhydroxide. And it's named after a German philosopher called Goethe. And his name is given to the rock, it's called Goethite. And that actually flows through the actual loose sediment and glues it together. So we get a hard rock. But it's not just this Goethite or clay, we can get things like the shells of animals, they dissolve. They are carbonate, so if you put a slightly acidic water with them, it will dissolve it, becomes a bicarbonate, and it passes through and glues it all together. And we'd know if it was carbonate because we could put a drop of vinegar on it and it would fizz. So all these sort of things are involved in converting this into that. So we're going to walk down. Ray, how are we going for time and things? What do you know? Oh, good. Because I want to have a look at some fossils if we can do so. Yeah.
This is kind of an out of the blue question.
Yeah.
How do you spell Goethe? Is that...
Goethite.
I just wanted to check.
Go to the philosophy.
Yes. Yes.
Same person.
On quite a lot of our rocks, you find things like little tubes. What are they?
Good spotting. That's exactly right. I'll give you the Latin name for it, or the binomial first, and then we'll have a chance to see some as we walk along the beach here. It's called Ophiomorpha beaumarisensis, the one here actually.
Like this, do you mean?
Let's have a look at that one then. May I just...
That's not quite.
No, that is a bit of Goethite. Now what it's done, it's formed around something that's no longer there. I have no idea what it was, but whatever it was, it's dissolved out. And that is the shell of the Goethite that's around it. That's quite a nice piece.
It's my son's from Mornington.
You don't want that here. All right, so we will, just out of curiosity, if I took a 1 cubic centimetre of sand, you know, this bit here, how many grains of sand of 1 millimetre in diameter would be in it? 10,000. No. Well, look, you know, you've got when you that's not bad because you go down 10 by 10 by 10. It's 1,000. Yeah.
That's how I work it.
Well, actually, it's about because that is if they are not close packed. They move in together. You get about 1,900. So I like to think about the fact that if we were to, you know, I like to think about numbers. Numbers are really fascinating. That's what makes the world around us. If we start, I did some calculations on a on a piece of old red sandstone that I'd collected in Caithness a few years back, and it's now in my garden. And I thought, you know, how far it's taken 390 million years to get from Caithness to my garden. That's how old it is. But how far has it travelled? And I thought to myself, this is a really interesting question to ask ChatGPT. So I asked ChatGPT, and it came up with the distance from Caithness to Beaumaris. So I said, yes, but surely the world has rotated somewhat in that time. Oh, apologies. It actually says apologies. And then it said the world has rotated so many times in the last 370 million years, so it's then travelled this far. And I said, thank you, but what about the actual movement of the solar system in space?
Oh my goodness.
So, and again, apologised. I was really amazed. It's probably learning from me now, but anyway. So what happened then was it told me, and I think it's travelled about 1 trillion kilometres.
Gosh.
Which is kind of fun, isn't it?
Did ChatGPT melt down after that?
Well, I love this thing with ChatGPT because my students used to love to plagiarise and so on, and it's easy to find out whether they have actually. ChatGPT, I really screwed it up yesterday, and I was telling a mate of mine who's a professor, and I said, look, this is what I did. I said, how many people were born in England from 870 to the present time? And it could not do it. I said, give me an approximation. And I said, that's what artificial intelligence is all about. It's supposed to do the really dumb things that you don't want to work out yourself. And it couldn't do it. It came up with formulae and things and said, I don't know. And I said, what? Well, I started by saying, you know, if we take something in every 30 years, add the population and a bit more to it, from 870 to the present time, and it said, oh, it's beyond my capacity. And I was, so we've got tubes. Now, what's really interesting about this is His Majesty's loyal City Council had a big poster up over here. Actually, it was Her Majesty's at the time when they put it up, but it doesn't matter. And on this poster, it said that these were the roots of Banksia trees that have been preserved. So you read something that is by an official body like Bayside City Council or Sandringham City Council as it was, and you think, that is what it is. Why would I ever question a city council? And the question is that a Banksia root? Well, for a starter, the rock we are standing on is marine. Now, not many Banksias live in the sea. Correct?
Correct.
So what you've got to do is you've got to sort of get the wheat from the chaff. You've got to look at the nonsense that's spoken to by people and say, well, is this a realistic interpretation? Is that it looks a bit like a root, except it's hollow. I mean, that's a big start, isn't it? If it's hollow, how many of you have seen a hollow root? Well, that's not one. That there, it's a tube, and we can follow them. Sometimes they go for quite some distance. I've tracked one for around about sort of 7 meters. And every now and then there's a vertical component. It goes up like that. So long roots like this, plus upward bits, doesn't fit. So what are they?
That's a marine worm.
Well, you're saying it is a marine worm.
I'm saying, could it be?
That is a worm.
No, could it be a worm's casting?
A worm's casting. Well, it's unlikely.
Okay.
Yeah. When worms, they don't normally do that. This has been made. It's a tunnel. And you can imagine whatever made it actually made it quite well. And it's typical of a crustacean. And they had their little pedipalps and they're pushing and so on. And you can see that the surface of it is papillate. It's got little knobs on it. And that's typical of a thing like a shrimp that's been pushing bits up and sticking them together with its saliva. And that's what it is. And the thing that makes it is an animal that's in the group called the thalassinids. and they are long shrimp, mud shrimps. They're very common today up around Darwin. But anyway, there is one there. That tunnel was made by a shrimp. The actual boring itself has been given this name Ophiomorpha. And because this one is typical of only this part at the moment, it's called Ophiomorpha beaumarisensis. Now, have a look at that, but also look at these other things around here. When there's patterns on the rock, by the way, you're standing on some Ophiomorpha there. See them there. This is one here. See it coming around there and going through there? And there's another one there that's been broken open, so we can see the inside of it there.
So is this similar to, because there's a whole lot of tubes like this down on the back beaches down at Rye.
Yes, yeah.
So same thing?
Same
It's
thing,
that
yeah,
shrimp?
yeah,
Wow.
yeah.
How big would it have been, the shrimp in reality?
About that long. And so they would have been able to move. You see that one there? It's been opened. Yeah. So they would have along there, and they would go up the vertical ones to come to the surface. But they weren't the only things that were here. A lot of the stuff. Yes, that could be, but that's not an Ophiomorpha. That's another type of animal. That could actually be. Somebody mentioned worms before. That could be a worm. There are certain types of worms around that are called Polychaetes. And see those yellow things, the yellow cream things on the rocks there, the living things? They are Polychaetes. And there is a slab, which we can't get to because of the tide, of fossilized Polychaetes. It's an area of around about 3 square meters. And you can see they were all like this. And in each one of the tubes, there was a little wee feet, or suri, beating away when it was alive. So it looks like we can't see many fossils here, except these rather impressive. They're called trace fossils or ichnofossils. And the reason why there are not so many shelled fossils is because they've been dissolved. There would be some here, perhaps, and we have found every now and then a beautifully preserved fossil of a thing like a sea egg, an echinoderm, where all of the carbonate in the shell has been replaced atom by atom by goethite. And I'll show you a picture of that later on.
We have nice soft sand rather than...
Well, I suppose the reason why there's sand here rather than pebbles is simply because this is part of a system, a cyclic system that's been continuously weathering and weathering and weathering. And when the stuff wears off, we're going to stop down here at this rock outcrop here. When this wears down, it doesn't form pebbles easily. But some beaches around Australia are just like the ones in England.
Okay.
But, you know, places like Brighton, for example, the English Brighton,
Yes.
there are just
Pebbles everywhere.
pebbles,
That's
that's
so
right.
disappointing going there, you know,
Yeah.
and it was you couldn't even sit on it. It was so whereabouts in Cork? I'm going to Cork in September
Oh yes,
to find my Irish ancestors. But
limestones, fantastic limestones.
and when I get to Cork, because I'll base there, and then I'm heading up to Killarney.
So your people are from Cork.
Well, I've only just found out that my 3-time grandmother came out as an Irish feminine.
I've been told I've got to speak faster, so I'll speak very fast now. See this here.
Yeah.
Now this is kind of fun because this is Ophiomorpha again, but it's been colonized by lichen, and it's slowly dissolving away. It's disappearing, and that when it breaks down will produce sand. Now, one of the ladies here just asked me a few minutes ago, why don't we have more pebbles on the beaches here? Well, it depends upon the nature. See, Australia is a relatively stable place. We haven't got rapid uplift like they do in parts of England, for example, where the rocks here are exposed and they weather slowly, and we have very, very quartz-rich sands. In certain parts of the world, you have everything still preserved. In other parts, and I'll give you one example, there's a place near Sao Paulo in Brazil where I visited. The beach sand is about the same colour almost as that red jacket there. And the reason why is it's made of garnet. And the rocks are very rich in garnet. They are metamorphic. And it just so happens that garnet is a very tough mineral like quartz, and it forms the beaches. It's really quite extraordinary to see pink beaches. But behind me is a cliff face, and Ray wants me briefly to mention cliff faces because they are so important. The reason why the cliff face, we can see it there, and there are much better ones further on, the reason why we can see this here is simple. It's because it's rapidly eroding. If it were not rapidly eroding, it would be like it is back over there. So even though we think about things being relatively stable, they are not. This is a bit more rapid than most places. And we've been coming along and doing beach walks here now for decades. Is it decades, Ray? I can't remember. It is. And a bit further along, there is a part where the entire steps had been undermined. And the council or Parks Victoria or whoever's responsible for it comes and fixes it up. But there is a constant erosion of this particular part of the coast. And that's natural. I mean, we should never believe that we can stop nature. Nature is constantly changing and eroding and evolving the coastlines around us. The reason why, as I said, we don't have the big pebbles here is because we don't have rapid uplift and erosion and new stuff coming out constantly. And if you have a look at the south-east coast of England, that's often what is happening there. There is parts of Britain is changing a lot faster than Australia. We're what's called an ancient craton that's been sitting relatively stable. And I know that some of you said that I was woken up last month by a pretty bad earthquake. Well, you ain't experienced anything if you reckon that was bad, because they get a lot worse than that. So, but Australia, very stable. That's why our beaches have white sands, the quartz-rich sands. Certain parts, if we go down around further south from the Mornington Peninsula and around the coast, the beach sands are almost pure white. It's because everything other than the quartz has been winnowed away.
What about somewhere like
Squeaky Beach, the good example.
like Flinders Ocean Beach, where you've got mushroom reef and you've actually got the little round pebbles, like the basalt, mixed in with the sand. Is that because of the basalt?
Well, the basalt around here is pretty new. That is the thing that's tossing the odd bits in that are different. Yeah. But what's really interesting is a lot of people look out here and they say, oh, these look like bits of basalt and so on. They are not. This is all sedimentary around here. Where did the iron come from? Nobody asked that question.
Good question, John.
Yeah. This young lady here, she says, where did the iron come from? Well, where do you think it came from? Queensland? Well, it could have come from meteorites, but it didn't. Well, I'm going to answer that one in a few seconds, but what's really interesting about the iron here, it came from volcanoes. Wow. The volcanoes around here are what we call ferromagnesium rich. They have dark rocks in them called basalt, and they are dark because they contain a lot of iron magnesium minerals. So they're iron magnesium silicates. And the goethite is the obvious byproduct of that. So when we have a volcanic eruption, there's a whole lot of stuff thrown up, sometimes tens of kilometers into the atmosphere. So if we have eruptions around Mount Lura and all around Victoria, there's going to be a lot of ash, and it contains iron. Now these rocks here were, as I said, deposited around about 5.5 million years ago from stuff like this here. They were then mineralized, but a lot of the changes occurred when they were uplifted, when groundwater flowed through them. There's not so much groundwater flowing when they're underwater. Now, I want to keep things moving. Ray suggested we should wander along. He's got another talk, and if I don't do it, I'll be sacked.
We couldn't have that.
No, so we'll walk a bit further along. There are tree trunks and things out here, huge ones.
But they are real ones.
They are real,
Ah.
but what's happened is they've settled on the seafloor, and they have actually left an impression when they settled.
Yes.
Then they have gone, they've been eaten by all sorts of animals, but before they left there was partial mineralisation of the rock, sand, tree interface, and we're looking at what we call casts.
Oh, so it's actually not the actual tree, but
It's a cast of the tree, yeah. So,
That's very good of you, John.
well, the problem with these ones is that I'm now, surprisingly enough, I'm past 40, and there's a rather interesting bit of controversy about Lavinia, the trivial name, which is wood's eye. Is it wood's eye or woodsy eye? And I think it's woodsy eye, but when I made these ones up here, I actually only put one eye. But these are embedded in plastic, so they're quite good if it rains. I do have some with the correct spelling, but they are on paper. So it depends what sort of a person you are. Whether you want the correct spelling or one that's embedded in plastic. So there we are. You can choose. So I'll put these out here, and so please, don't all rush. You don't need to take one. The other thing I've got is this here, which may fascinate you. I got this off the web the other day, and it's Lavinia Wood's Eye are for sale at $284.98 each. So when you pick up one of these, we will accept $100. But this just goes to prove there must be people out there who are pretty gullible, who are prepared to pay that.
So you pay.
And the indigenous collection in each of the branches is brilliant.